Okay. Well, I think it's a good idea to start with x1, and the reason I think it's a good idea to start with x1 is because we've got a control input for x3. Okay. So that's going to be the last thing we design because this is our actual control input. And this is going to be the thing that kills all the backstepping errors and gives us our final goes to 0 stuff. Okay, so we would never want to start with this one. So then the idea would be that by controlling u, we could make x3 do what we wanted it to do. So if we can make x3 do what we wanted it to do, we can make x2 do what we wanted it to do. And then if we can make x2 do what we wanted it to do, then we could use this as kind of like a control input to maybe make x1 do what it should do. Right? So this is kind of like the base level. So maybe we should start here and start trying to define what our desired input would be here so we would know what our desired input would be here so we'll know what our input can be here. All right, so x1 dot equals ax1 squared plus x2. So Parag, you said you defined 2 backstepping errors. So you defined one for this error system. And what was that backstepping error? Okay, x2 minus x2d, which means we have x1 dot equals a x1 squared plus x2 plus x2d minus x2d. Okay, so this term and this term are the backstepping error a to 1. So x1 dot equals a x1 squared plus a to 1 plus x2d. So now we want to design x2d. And let's start, anytime we start doing design, let's go ahead and also start doing a Lyapunov function. So
it would be perfectly valid to call x1 dot e dot, right? Or if our control objective is to drive x1 to 0, we could have an error that's x1 minus the desired point, but the desired point will be 0. So e would equal x1.
That's absolutely true. Yep.
Okay. Just making sure that's not completely off base to say that.
Okay, so what's going to be the first term in our Lyapunov function? So, Ken, in case you didn't hear Darren's question, Darren asked, would it be okay to define an E1, which is an x1 minus a constant set point, in this case 0, and then express this in terms of E1 dot? And the answer is yes to that. So, what would be the first term in our Lyapunov function here? Yeah, how about x1 squared? We want to show x1 goes to 0, so let's throw that up there. Then we've got our first backstepping error, so we know a second term that should go in the Lyapunov function, right? So we also know that we're going to probably need a 1/2 a to 1 squared up here, because we're going to want to show the backstepping errors go to 0 also. All right, so now that we kind of are foreshadowing to the Lyapunov analysis, now we can start thinking about design at the same time. All right, so someone tell me how they designed x2d. Keith Dupree, did you get a design for x2d?
Still kind of working on it.
Okay. Keith Stegath, did you get a design? Don? Chris? Roger?
We make x2d to make the first equation have it as
Yeah.
we then define minus ax1 squared and then minus k.
Minus kx1. Okay. So I thought this ax1 squared was going to be a good term. Why did Roger cancel it out?
Was the derivative of this a negative?
Exactly. We don't like even powers. It looks attractive here. Maybe even a was negative. But because you've got an even power here, when I put this in the Lyapunov function, look, I'm going to have x1 times x1 dot. And if x1 dot has an even power, then I'm going to get another x1, I'm going to x1 cubed. Okay, so odd powers are good, even powers are horrible. Okay, so that's why Roger said, well, I hate that term, let's get rid of it. Minus a x1 squared. Okay, then why didn't he do anything about a to 1? We're probably going to take care of that one in a little bit with a cross term. We don't have to worry about a to 1. And then it's clear the motivation for the minus kx1, right? Because that's going to give us our feedback term. So if we substitute this in here, then our closed loop error system is going to be x1 dot equals a to 1 minus k x1. Okay? So we go over to our Lyapunov function, and we got minus k x1 plus a to 1. Okay? Love this term. Really don't like that term. So now we got to work on this a to 1 dynamics. Okay? So eta is x2 minus x2d. So a to 1 dot is equal to x2 dot minus x2d dot. So let's step back a second and look at our control design so far, and let's check if we can implement this. Okay, it's got a was known, and it's got x1 was known. Okay, looks good. A to 1 dot is equal to x2 dot minus x2d. Okay, x2 dot was equal to x3 minus x2d dot. Okay, so I'm going to pull out this minus sign with this minus sign and make it positive. Well, no, let's just keep it straight. Minus the derivative of minus a x1 squared minus k x1. All right, so Parag, you said you defined another backstepping error. What was your other backstepping error? So why did he choose x3 and x3d? Well, because if we have another backstepping error, we take its derivative, so now we put like an a to 2 in the Lyapunov function, and then we try and find the closed loop error system for this, and we get an a to 2 dot is going to equal x3 dot. Because x3 dot's where we want to be, right? Because that's where our actual control input is. Okay, so that made sense that we're going to want to get that actual control input in here, so x3 minus x3d. So that means we add x3d minus x3d. Okay, so that means a to 1 dot is equal to a to 2 plus x3d minus the derivative of minus a x1 squared minus k x1. All right, so let's go ahead and examine this term. So this is going to equal to negative 2a x1 dot minus k x1 dot, which is equal to negative. All right, now I'm going to just go ahead and pull the negatives out, which is plus 2a x1, and x1 dot was equal to a x1 squared plus x2. Oh, wait. 2a x1 plus k all times x1 dot, which is a x1 squared plus x2. Okay, that was just algebra.
Why is it that we wouldn't use the x1 dot there, a to 1 minus k x1?
We could have. there and ask, why didn't we use our closed loop error system? And we could have. All right, so now let's design X3D. Well, now when we design X3D, let's think about the Lyapunov analysis again. We've added another variable transformation, right? We've added another backstepping error. We added a to 2. So we need to come back over here and have a 1/2 a to 2 squared. So then we're going to have an a to 1 times a to 1 dot. And we're going to have an a to 2 times an a to 2 dot. All right, so thinking about what we want to have in a to 1 dot, what should we have for X3D? Come on, don't be shy. Just go ahead and yell something out.
You can cancel the big term in that one equation.
This term?
Yeah.
I'm going to call this W for simplicity. Is everything in W measurable?
Yeah.
Measurable and known, right? So we know everything about W. So Roger says, well, that's a bunch of garbage. Let's get rid of that. So minus W, that's a good idea. Minus K2 a to 1. Is that a good idea? That's our feedback term. We've got to have that in there. Now there's one more term missing. What would that be? Minus X1. Backstepping cross term right there. Cross term. Excellent. All right, so we plug that in there, and we get a to 1 dot is equal to a to 2. No one said anything about a to 2 because it's another backstepping error, and we're just going to let it float through, right? Okay, minus W. Well, W just took care of all this business that we didn't like. Minus K2 a to 1. That's our feedback term. And then minus X1. Okay, and this was motivated from the Lyapunov analysis. So now if we go plug this into our Lyapunov analysis, we get minus K2 a to 1. There's our feedback term. We love it. Plus a to 2. Not a big fan, but we've got a to 2 sitting down here, which is okay. And then minus X1. Okay, great. It was a good idea that we put this term in there, because now that term cancels that term that we didn't like. Okay? So we're cool up here, we're cool right here. Now our problem child is this plus a to 2, but we've got our a to 2 dynamics just waiting for us to take care of it. All right? So a to 2 dot is equal to, a to 2 is x3 dot minus x3d dot. Okay, which is equal to u minus minus w dot minus k2 a to 1 dot minus x1 dot. Uh-oh. This is the old problem with backstepping. We've got these higher order derivatives in here. You know, w was okay. We had x1 dots in here, which scared us initially because x1 dot was an unmeasurable state. But we could substitute in for x1 dot and rewrite it just in terms of x1s and x2s, where x1s and x2s are measurable. All right, so we know x1 dot's not a problem because that's got x1s and x2 stuff in it. A to 1 dot, well, a to 1 dot had x1 in it, and it had x2 minus x2d, x2d just had x1s in it, so that was okay. A to 2 was equal to x3 minus x3d. Well, of course, everything in x3d is measurable because it has to be since we design it. And x3 is known, so a to 2 is known and measurable. So a to 1 dot's going to be okay. But we've got now w dot sitting there. But if we look at what w is, we're going to get an x1 dot term. That's okay. We're going to get another x1 dot term. That's okay. Now we're going to get an x2 dot term. But x2 dot was equal to x3, right? So we're okay. Whew. It was scary. We had to check it because it's always a problem with backstepping. And many a paper have been rejected because of this issue. And many results have been crumbled up and thrown in the trash because of this issue. But because x2 dot equals x3 and x3 was measurable, then we're okay. W dot contains all stuff that's known and measurable. All right, so now we have to design our U. U is pretty trivial. How are we going to design U? Quickly, because I've already got the one bell going. Minus W dot. Okay, so Chris got rid of that term. What about that plus K2 A to 1 dot? Let's get rid of that one with the minus K2 A to 1 dot. How about the plus X1 dot? Let's get rid of that one too. Minus X1 dot. We've got to have one of these feedback kind of terms. Anything else? Cross term, right? We left an A to 2 dangling over there. Okay, so we got an A to 2 times an A to 1 positive. So we need to have a negative A to 1 term there. Is that clear? Julio, do you understand why we put that there? Great. All right, so if we do that, then A to 2 dot is equal to, that crosses out, that crosses out, that crosses out. We get minus K3 A to 2 minus A to 1 minus K3 A to 2 minus A to 1. Okay, here's our minus A to 1 plus A to 1 A to 2 term. Our cross term, we have to cross off the cross terms. So what are we left with? Minus kx1 squared, minus k a to 1 squared, minus k a to 2 squared. What do we have? Guess. Does anyone have a question about why we have guess? Roger, do you have any questions about why I have guess? Okay. Sean?
Yes.
Do you have a question about why we have guess?
Yes, about how do you see exponential.
All right, so V can be upper bounded by 1/2 norm z squared, where z is a vector of x1, a to 1, a to 2. And V dot is less than or equal to the minimum of k, k2, k3, all multiplied by the norm of z squared. Okay? And so now I use this equation and say z squared, I say the norm of z squared is greater than or equal to v over 2. So in here we need to put something smaller than norm of z squared to make this a sufficient condition. And so we put v over 2, and so we get v dot is less than or equal to the min of k, k2, k3 over 2 times v. So there's my exponential, and my rate of decay is given by the minimum feedback gain. Okay? So this is yet another backstepping example. And on Wednesday, today's Tuesday? Wednesday, today's Monday. On Wednesday, we'll do our final backstepping example. That's explicitly backstepping, I guess. And we'll talk about high gain current feedback. Okay? That's it.